Chemical reactions are such a fundamental part of chemistry. Thanks to the discoveries and observations of Lavoisier and Dalton, chemistry has come from literally playing with fire to now a very systematic and quantitative science, where we not only understand how a chemical reaction works, but we can manipulate it in just about any way we choose. Chemical reactions are everywhere in nature. Our bodies are run by biochemical reactions. Trees produce their own energy by photosynthesis, and neon signs are actually a chemical reaction. All of these things can be represented by a chemical reaction equation. Most reactions have many aspects that are observable. Some reactions will release some light as part of the product. That's a flame reaction or fire. Many reactions will actually produce a solid or a milky substance that's called a colloid. Well, that's actually a precipitation reaction. Gas evolution reactions are another type, and those are very, very common, especially in automobiles. That's a combustion reaction. It's where a gas is released as part of the product. So it's actually a phase change, just like the precipitation reaction, where the product now has a different phase than it started with in the reactant side. So a gas is released in a combustion reaction, or in the production of hydrochloric acid or sulfuric acid. Those are gases that are now redissolved in the liquid. One of the most interesting parts of studying chemical reactions is the huge variety of different applications that they can have. Here's a rock quarry where this company is extracting various kinds of rock and potentially ore from this area here, and it's going to go through so many different processes to extract valuable minerals or rock for construction materials like concrete aggregate. So what can happen here is some of this ore can be sent off to another plant where a process called smelting is used. So they'll heat up the ore, heat up the rock that they have, add in some reducing agent to drive off all the oxygen. These metals are usually metal oxides in ore, and so driving off the oxygen gives you that metal that'll come out of the rock after it decomposes. So before we can get started having some fun with some of these chemical reactions, it's a good idea to get some concepts out of the way first. One of them being chemical reaction classifications. This is dealing with classifying what actually is going on with the molecular rearrangements during the reaction. And then also talking about chemical reactivity. So metals are just super common in chemistry, and so it's been well studied how these react with water and also acids. So in terms of classification of reactions, there's two similar ones here, the decomposition and the combination reactions. Decomposition is, well, it's just a molecule that's kind of falling apart into two pieces here. The combination reaction is the other way. It's two molecules coming together, two atoms or molecules, it can be either, and they just make one single compound here. That's molecular oxygen and molecular hydrogen forming liquid water. A little more interesting types of reactions are the displacement reactions. So with single displacement, one option is you've got a solid metal here, solid magnesium metal. If you put that in acid, hydrochloric acid, well, the acid will actually, break down the metal just like you'd expect with acid. But magnesium will take the place of the hydrogen on the HCl molecule. So we end up taking the place of hydrogen there, and you end up with molecular hydrogen as one of the products. Now, this can be kind of hard to tell because we've changed just a plain old H to H2 now. So really the key to this is looking over here at the product, this little salt here, and seeing that these two are now together, but just these two, just a single swap. A little more complicated then is the double displacement. That is where now both the anions and cations of each molecule, or well, in this case just two molecules, both of them now swap places. So, in case of phosphoric acid here, we've got three hydrogens. They will swap places with these three sodium ions. And of course, the phosphate will swap with hydroxide. Now we've got another case here where we've made something completely different. Rather than just swapping the element in front of the molecule name, molecule formula, we've got a whole different molecule. So again, it's easier to look at the salt that's formed. So in terms of how well these reactions occur, especially talking about metals, metals can be violently reactive, like sodium and lithium. If you've ever seen a demonstration of even just a small couple grams of sodium being put in plain water, it's explosive. You actually can't store that in any kind of container other than one that's filled with some kind of oil, something that's moisture resistant. Otherwise, it will actually catch on fire. So a lot of scientists noticed this, and they started measuring kind of how quickly a metal dissolves in water, or how explosively it does, because it is dissolving in it just rather energetically. And they've built, and some of these were calculations as well, and they've built a series here. It's the reactivity or activity series, depending on who you ask what it's called. And it's talking about again, that general reactivity. There's really no good way to describe that other than how quickly the reaction finishes. But starting at the bottom here, these are the least reactive. That's silver, gold would be on here, lead, mercury. These are all not very reactive, according to this list here. And the top, we've got our favorite lithium and sodium. You know, they react directly with regular water. You don't have to do anything to them, and they're very vigorous reactions. If you move on down just a little bit, you have to actually put a little bit of energy into these. So they're not as reactive, but you can make them react pretty well if you just add a little hot water. And then if you add acid to the weaker ones, that will react, of course, very well. So the actual, founding principles of this idea aren't really well known, but you can look for trends on the periodic table to at least help you kind of follow other trends that you're very familiar with and relate it, or even help you memorize some of these trends. The electronegativity is always a common trend that's associated with many other chemical concepts that aren't really well understood, but we know that it's related to electronegativity. I'll show you that in a second. But this is actually really useful. Other than just seeing cool explosions, it has a very nice practical aspect, because you can take advantage of the differing reactivities of the metals that you know are in your ore or some other rock that you have, and you can extract them piece by piece. So it's very useful to take advantage of. It's very similar to the rock quarry, actually, that I was showing you earlier. It's commonly used methods. This is another relation between electronegativity and reactivity. If you notice over here on the left with the alkaline and alkali earth metals, they're very low electronegativity. These are very large molecules, large atoms actually. This group here, they have fewer protons, so they have a larger radius. So really just handing out those electrons. They're just putting them way away from their body, way away from the nucleus. But as you go across, you increase in electronegativity, and you have these metals over here that are very unreactive. And that kind of makes sense. We've got gold and we've got silver. Well, jewelry is made out of those. So those are made out of silver and gold because they don't tarnish very easily, and they don't react with other things, so you can accidentally get them wet. They don't rust or anything. Platinum and palladium, those are catalysts used in a great number of industrial applications and in your car actually. But if those reacted really well with other compounds and made new compounds, platinum actually combining to make a platinum compound, that would actually be bad. Your catalyst would be done. So these metals are very unreactive, and that's why we can use those as catalysts now.